Hey guys, Mr. Smith here. No embedded webcam for this video lesson. We are going to be doing a 2D acceleration problem together. So it might take 20 minutes or so, and we're going to use two methods in the problem we're looking at today. Much like we've done other methods or other questions, two ways, just to give you guys some choice. We'll be applying trigonometry and also using components of vectors. So let's get started. Here's the problem we're looking at. We have a lawnmower kind of mowing around a kidney-shaped garden, and the lawnmower is moving at a constant speed of 1.8 meters per second. Now, acceleration occurs when the velocity of an object changes. In one dimension, that might mean like it's speeding up or slowing down. But in two dimensions, like on a plane, that could just mean the object is changing direction. So I think it's kind of a loaded question, but for this lawnmower, is the lawnmower accelerating? And the answer is yes, because it is not moving at a constant velocity. It might be moving at a constant speed, but as its direction is changing, as it mows around the outside of the garden, if its direction is changing, its velocity is changing the direction, and acceleration is occurring. So what we'd like to find is that average acceleration. So we have a change in speed here, and we're going to say that the lawnmower takes 4.5 seconds to get from point A to point B. And we're going to find the average acceleration. And acceleration is a vector. We are going to find the magnitude and direction. And as we're still kind of starting out in the course, we won't always do questions two different ways, but we'll do this question using two methods, just as a good review exercise. Just one more example in the books for you guys to choose a method you'd like. Later on, we might, for different problems, one method or the other might make more sense, and we'll just do problems one way. Now, the definition of acceleration is change in velocity over change in time. And change in velocity is the final velocity minus the initial velocity. So it'd be the velocity at B, subtract the velocity at A. And here we have to review, or maybe you've never subtracted vectors before. We know how to add vectors. You add them tip to tail, but how do you subtract two vectors? Well, subtracting vectors is easy. To subtract vectors, you add the opposite. So I'm going to, just as a bit of an illustration here, you can add this to your notes if you'd like. Just going to draw two just general vectors. I'm going to call that vector A, and I'm going to call this guy vector B, pointing to the right. If you want to and you're following along, can you draw the vector A plus B? If you added those two vectors together, what would that look like? So you can pause it at home if you'd like. Give that a go. I'm going to do it over here. So to add two vectors, you draw them tip to tail. So you draw vector A, and then where you end A at the tip, you place the tail of B and you draw B. And the resulting combination of vectors from here to here gives you the vector A plus B. On the same diagram here, I'm going to show A minus B. So to do A minus B, you draw A, but then instead of drawing vector B, you draw its opposite. If I go out this way, this is the opposite of vector B, minus vector B. And the vector starting from where I started A and ending at where I finished off negative B, this is vector A minus B. It's the same as if I did vector A and I added the opposite of vector B. So, that's just a quick crash course in, how to draw a subtraction of vectors. Hopefully you got to do some of that with your grade 11 teacher when you took that course. So the first way we're going to solve this problem is we're going to solve this problem using trigonometry. We're actually going to use vector subtraction. We're going to draw the actual vector diagram and use that to solve the problem. So just flipping back, we have to draw the vector VB plus negative VA. We got to find that resulting vector, and then we can divide by 4.5 to get the average acceleration. So here we go. So maybe just off to the side, I'm just going to write a little reminder. So for the average acceleration, we're doing VB minus VA divided by delta t. So we're going to draw the vector VB. So vector VB looks, I don't know, something like that, right? Going up and to the right, vector VB. Now VA goes down this way, right? Negative VA is going to point back up this way. Negative VA. And what we're left is, this is going to be our, I'm just going to call this delta V just to save a bit of space. That's VB minus VA. So we've drawn our diagram, our vector diagram. And let's add what we know into this diagram. I'm just going to use a different color, maybe use green. So we know the length of the two of those sides. VB, the size of that velocity vector, is 1.8 meters per second. So just I'm going to tuck in 1.8 meters per second there. Now VA, we also know is 1.8 meters per second. Remember, it's not negative 1.8, where the magnitude of a vector is always positive. And the size of how long that vector negative VA is, well, it's the same length as VA. It's also 1.8 meters per second. And we do get here an isosceles triangle. We like to find delta V. To do that, we do need to have an angle in this triangle. So we are going to use some of the information from the question to do that. So I don't want to make my diagram too overly complicated. So maybe I'll actually, maybe what I'll do is off to the right here, I'll maybe just draw a scaled up version of our triangle. And just do some rough work over here, and then to verify what an angle in our triangle is, and then I might erase it afterwards. I'm just going to draw a dashed line representing like the compass rose. And I might actually also include a little dashed line illustrating VA. So what do we know from the problem? So we look at VA. Vector VA is 1.8 meters per second, 27 degrees south of east. So I know that this angle here will be 27. And due to opposite angles, I also know that the vector negative VA would be 27 degrees north of west just by that symmetry. What do I know about VB? VB is 15 degrees east of north. So this angle here is 15 degrees. And from a Z pattern from our grade 9 math courses, we know that this angle would be 15 degrees. And if south and west make a 90-degree angle, I know this angle here is 75 degrees. So if I put all that together, 27 plus 75, I get a 102-degree angle inside this triangle. So now that we've worked that out, maybe you copy this into your notes. I'm just going to actually erase that. It's going to be there. You can pause the video and go back to it if you like, but I'm just going to create more space for me to actually finish my solution off. So we had to use all that directional information to reason that angle out. But now we've turned it into a grade 10 trigonometry problem. We're going to be using the cosine law. To find the change in velocity, its magnitude. So So cosine law says we will square root 1.8 squared plus 1.8 squared again, minus 2 times 1.8 times 1.8 times the cosine of 102. So you do that at home. I'm going to do it right now as well. Squared minus 2 times 1.8 times 1.8 times the cosine of 102. And don't forget to square root. So that I got, for the size of that change in velocity, I got basically 2.8 meters per second, which seems to fit, doesn't seem so outrageous. Now, what about the angle? Now, something I didn't mention is, it's not terribly obvious whether the change in velocity, because I didn't draw a scale diagram, whether the change in the way I drew my my diagram, I drew it so that delta V appears to be going kind of north and west, but it is not a scale diagram. So, my vector, delta V, it could be pointing straight up, or it could be pointing kind of east of north. We won't really know until we find this angle. So let's find that angle. And because this angle is 102, I know it's acute, so using the sine law will be just fine here. So sine theta over 1.8 equals the sine of 102 over delta V, which we got was 2.8. Now, just as I was setting this up, I was thinking, actually, if this is an isosceles triangle, we can actually figure out what these two angles are, because the angles in a triangle add to 180. So if we do 180 minus 102, and then cut that in half, that should give us what theta would be. So that's 78 over 2. So it's 39. But just for fun, let's finish this off. So we would do, to get sine theta, we would do 1.8 times the sine of 102 divided by 2.8. And then we would do sine inverse to get the angle theta. And sure hope we get 39. Be a little bit awkward if we don't. Dig back and find out where my mistake was, but it will be good, I believe. 1.8 times sine of 102 divided by 2.8. Shift sine. Yeah, so very near 39 degrees. So we're almost ready to answer the question. It's just that 39 degrees, that's the angle that delta V makes with VB. It's not exactly a compass direction. So we just have a little bit of work to do. So before I write a final statement, I just might make a diagram up here. So here is VB. It was 15 degrees east of north. And we just found that our delta V vector pointed off this way, definitely not to scale, but that this angle, this entire angle, was 39 degrees. Well, that just makes this leftover angle 24 degrees. And we can now state the direction of delta V. So delta V is 2.8 meters per second, and its direction is 24 degrees west of north. And that allows us to get our average acceleration, because that is the change in velocity over the change in time. So we take 2.8 meters per second, and we have the same angle, 24 degrees west of north. And in our question, we said it took 4.5 seconds to have that change in velocity. So 2.8 divided by 4.5. So about 0.62 meters per second, or meters per second squared. And the direction of the acceleration, 24 degrees west of north. We've got it. So if you really like trigonometry, you don't have a problem drawing that vector diagram and using the compass directions to reason out angles in the triangle, then yeah, trigonometry works good. It's just two vectors, so it is possible. But maybe you like using the component method. So let's solve this problem a second way, now that we know what the answer should be. let's use vector components. So we're going to use a sign convention that north is the positive y direction and south is negative, and to the right is a positive. So to the east, or the right on our page. So east is positive and west would be negative. And we got a diagram here, kind of already breaking down the each vector into components. We still need to subtract those two vectors. We're still doing VB minus VA. We still have to understand the vector subtraction. But now we know we can just kind of add these two resulting vectors together, and we're going to get something that's going kind of up and left on our page or northwest. So let's begin. Let's do VA. So VAX. So there's a couple ways we could do this, and you can just do kind of whatever you feel comfortable doing. What I'm going to do here is I'm just going to find the magnitude of VAX, and I'm then just going to pop. Understand that VAX is pointing to the left, so I know that my sign should be negative. So VAX. Actually, you know what? I'm just going to call an audible. I might save it afterwards. I might just do it this way. We'll see how this works. We know VA is 1.8. And our angle beta is from our work from earlier was 27 degrees. And because VAX is adjacent to that 27 degrees, we're using cosine. So 1.8 times the cosine of 27 degrees. And I'm actually just going to leave it like that for now. And we'll see how you guys like this method. So if I do VAY, it will be 1.8 times the sine of 27 degrees. And again, I'm going to leave that as it is for now. Let's look at the next one. This is interesting because this is a bit of a switch from how we've been doing things. The angle we're given is 15 degrees east of north. And if we're trying to find VBX, that x component, VBX is opposite the 15. So we'll be doing, and remember, VB is 1.8, just like VA was. And so we'll be doing 1.8 times the sine of 15 degrees. If you want to be always x is cosine, y is sine, then you would need to be using 75 degrees. But here we'll just use the 15 just to mix it up. And VBY will be 1.8 times the cosine of 15 degrees. So let's add these components together. So for my delta V in the x direction, so what do I have? I have VAX going in my negative direction, and I have VBX going in my positive direction. So I will be doing VBX. I might just actually, yeah, I can do this. VBX, and I'll be subtracting the number I got for VAX. 1.8 times sine 15 minus 1.8 times the cosine of 27. Now, of course, if you just prefer just to find those values earlier, that's okay. 1.8 times sine 15 minus 1.8 times cosine 27. So what we can see here is the x component, and I'm going to keep just a bit of accuracy to make sure our answers line up with the first method. We get negative 1.14, which means our change in velocity and our acceleration will be to the negative x direction, which is west, which makes sense. We already knew that from our previous work. Let's find the y, and then we'll combine those two vectors together. So visually, you can see that both VB and negative VA are pointing up, right? So we'll be adding these two guys for the change in the velocity in the y direction. So delta Vy will equal, VAX or VAY plus VBY. They're both pointing straight up. They're both positive. So we have 1.8 sine 27 plus 1.8 cosine 15. And let's see what we get. Again, I'm going to keep just 2 decimals just to keep some accuracy. I want to make sure for you guys that my answers are identical. And we get 2.56 meters per second. So I'm going to flip to just a new screen, and we'll combine these two guys together. Let's draw what we have. So our delta Vx, or sorry, our delta V is something like so. Established that earlier. What we've just found out is that delta Vy is 2.56 meters per second, and delta Vx is 1.14. Its size is in that direction. So these are side lengths and triangles. That's why I'm writing them as positive, because I'm drawing a triangle of my vector components. I'm going to recombine them. So if we find the hypotenuse of this triangle and the angle at the bottom here, hopefully they match up to what we found earlier. So what is the size of this delta V vector? This is the root of 1.14 squared plus 2.56 squared plus 2.56 squared. And don't forget the square root. So we get about 2.8 meters per second. And the direction, we will use tan. So we'll be doing the inverse tan of opposite 1.14 over adjacent 2.56. Second tan. And look at that, 24 degrees. Life is good, guys, because if I flip back to our method 1, delta V, we got, for the size, we got 2.8 meters per second. And for our angle, we had to work a bit for it, but we got 24 degrees as well. The component method kind of got us there. You know, if you just maybe with a little bit less complicated diagrams and math, or honestly, maybe you felt that that was more involved than just drawing a triangle of the vectors and using trigonometry. But the nice thing is you can choose. Any average acceleration question just involves a final velocity and an initial velocity, 2 vectors. So both methods would work pretty well. And so just finishing this off, actually, we get the same delta V. I'm just going to write same as before, which means the acceleration is the same as before too, right? We don't need to redo those calculations. It all worked out. So just a good little exercise there, finding a 2D average acceleration, reviewing some vector skills, specifically subtracting vectors. And then we solved the problem 2 ways. Again, just getting some practice using either method. And now moving forward, you can kind of choose the method that kind of clicks with you. What are we doing next? In our next lesson, we're going to talk about relative motion in 1 dimension and 2 dimension. So it should be pretty fun. I hope you guys are staying well. I don't know whether you'll see my handsome face for the next video lesson or not. See if I can get my software to work. But that's okay. You'll at least be able to hear my soothing voice. Stay well, guys. We'll see you soon.